I think it's important for all of you to share very intimately with me what I do in the way of conscious disciplining myself as we meet. I am an experientialist. That is my grand strategy, which I'm discussing with you, of coping with problem solving, is one which has an important name, operational. The word name operational came to be applied to science, I think, it was the invention of Percival Bridgman at Harvard, a natural philosopher at Harvard, who invented the term early in the century when Einstein made his first announcements. And Percival Bridgman at Harvard, as a natural philosopher, said he was deeply interested in how it happened. Science, in general, was caught so off guard, so unexpecting of Einstein's kind of a pronouncement and the viewpoint that was demonstrated by Einstein. And he became a great student of how all the circumstances surrounding Einstein's developing the thoughts that he had developed. And he then found that Einstein was concerned with all, not just some data that was discovered in an experiment, but all the circumstances surrounding that faithful reporting of the immediate, local, intimate conditions under which the discovery was made. And I will come back to that, but give a working demonstration of why Einstein felt it was so important to record all the circumstances as well as that which was specially isolated out and discovered. The example that I'm going to give you is my own invention, but I did include Einstein and Einstein's philosophy and my own interpretation of how he came to develop his equation and other of his strategies in my first book, Nine Chains to the Moon. And because I had three chapters on Einstein, my publishers, who were Lippincott of Philadelphia at that time, this is mid-30s, about 1935, said that they found that I had three chapters on Einstein, and at that time there was a sort of a general myth that there were only 9 people in the world who could understand Einstein. They said they looked at all the lists of people who understood Einstein. I was not on any of the lists. In fact, they didn't find me on any list and of any authority, and they felt that for me to be writing 3 chapters on Einstein would make them, Lippincott, be accused of being a partner to charlatanry, that I was just a fake. And so I was a little stung and was still quite young, and so I simply wrote back, in a sense quite facetiously, to Lippincott, saying that Dr. Einstein had just come to America and was in Princeton at the newly organized Institute for Advanced Study, and I suggested they send my typescript to him, that he would be the best authority. I really did not think they would take me seriously about that, and I forgot all about it. And it was about 6 months later that I had a telephone call from a doctor in New York, and he said, my friend Dr. Albert Einstein is coming in to spend the weekend with me, and he has your typescript, and he would like to talk to you about it. And could I possibly come on Sunday evening to his apartment in New York? So you imagine I didn't have any engagements that would interfere. And I had very few engagements in those days. everybody wanted to talk to me. And I did come then to the apartment, and it was a wealthy man, and he had a large living room, and in more or less Germanic kind of style. People were sitting around the walls of the room, and he was sitting pretty much in the middle, and I think later on he might have played music for them. And when I came in, I was brought then to this long room up to meet him. And I really had, I don't know how much is psychological within me, but I really had the most extraordinary feeling of being in a presence of almost an aura of him. He immediately excused himself from the company and took me out to a little library that was just off the main hall of the apartment. And on the library table was my typescript and under the light, and we sat down on the other side of this desk, and he said he'd been over my typescript, and he was writing to my publishers to say that he approved of my interpretation of his thoughts in the way in which I had explained his translation of philosophy, a philosophy of his which had been published in the New York Times Sunday magazine New Year 1930, called The Cosmic Religious Sense. It's a very, very inspiring piece, and I had asked the publishers if I could quote it in my book, and I did. Having then this chapter on his philosophy, I then had another chapter on the way I felt that he interpreted into how he applied that philosophy to all of his own grand personal strategy of his life, and how he came about developing his thoughts on an equation. Then I had a third chapter, which I said that historically great scientists, individual scientists, make discoveries. The Academy doesn't accept right away. Later on they do accept. Then it gets to be in the schools, and this gets to be into the in the general atmosphere of everybody's thinking. At this point, engineers and inventors within that atmosphere of thinking make some invention, and then gradually some industry takes on that invention. That takes quite a while. There's a lag. Finally, various things are being produced, and which bring about a new environment under which social changes have to occur, and politics then has to take care of the take-up on the new orientation of man, all brought about indirectly from the original scientist thinking. And I said, then my third chapter was, I developed a hypothetical picture of how humanity would be living. It was called E equals MC, second power, equals Mrs. Murphy's horsepower. And then I was looking at the everyday life of Mrs. Murphy under the circumstances of everybody really being completely convinced of the validity of Einstein's thinking. His equation had not as yet been validated as it was later by fission at the time that I was writing. Anyway, he said he did approve of my two chapters, my chapter explaining how his philosophy was interpreted in his action, his thinking. But he said this third chapter about Mrs. Murphy's horsepower, and his words were, I will imitate him because I remember this so very well, and he was very gentle, and he said, this third chapter, young man, you amaze me. I cannot conceive of anything I've ever done having the slightest practical application. And he went on to explain that he had evolved his thoughts as possibly being useful to the astronomers, to the astrophysicists, to the cosmogonists, and the cosmologists, but that it didn't have any practical application, nothing. And right, he did approve, and they did go on with the publishing of the book. This is very interesting because this meeting occurred about a year and a half before Hahn and Stresemann and Lisa Meitner discovered theoretical fission. And then there was a whole set of events which followed, which most people are very familiar with, and then the German scientists, Jewish scientists, getting the word as quickly as they could out of Germany, because they thought it would be used immediately for armaments in Germany, and the word did come to America, and there were theoretical studies, and then came the conclusion of the scientists that fission was actually possible. So there was the quandary of the scientists, and how, because politicians don't listen to the scientists, on how to get word to Franklin Roosevelt. So they all decided that Einstein was by far the most highly accredited of scientists, so they asked him to go to see Franklin Roosevelt, and Franklin Roosevelt did appropriate what at that time was an incredible amount of money, $85 billion for the Great Manhattan Project. And then ensued then the Enrico Fermi pile, with all of which history most of you know. But it was interesting to me that I heard from this man 2 years before the theoretical fusion is envisaged, that he did not have any slight idea that anything he had ever done would have any practical application, because the first practical application of the Enrico Fermi pile completely validated his theory of the amount of energy that was being stored in a given mass. So the very essence of what was going on. So the first practical application was Hiroshima. And having heard that from that man just before this occurred, I realized the unhappiness and the consternation that he experienced when the first practical application was Hiroshima. In fact, his last days were spent greatly devoted to trying to get the scientists to realize their responsibilities and how they were being exploited, and brought about his consternation, brought about the development of there was an Association of Atomic Scientists and the publishing of the Atomic Scientists Bulletin and so forth. And he expressed himself very vigorously his great unhappiness about this. But to have heard from that man before he realized that it would be a practical application, it would come in the political field, was a very extraordinary experience. But I do have then the personal confidence that when I interpret Einstein and talk about him, which I do very frequently, I did have his personal approbation of my capability to do so. So I'm giving you then a hypothetical example of what Einstein employed as a strategy of thinking, which brought about Bridgman's development of the word operational. Now, I'm going to give you then a man in a railroad train going west across the desert, and his train is going very fast, and he leans out of the window and drops a flaming apple. And he has a friend with him and so forth, they have a sextant to measure angles, and they have stopwatches and so forth, and he observes what he sees in the total azimuth of observation of the angle in which this light forms. Obviously the flaming apple goes the opposite direction from him, and he sees it doing that, and he records his stopwatch exactly what angle of motion there was, some totally, as he looks back at it here, going back like that and a little back towards the track. And he has a stopwatch reporting exactly how long it was in each of those positions of the various azimuth observations. Then we have another man who, at the same time, was standing way to the north of the train, was going west in the desert, and he had his observation instruments, his angle measuring device in his stopwatches, and he sees the flaming apple go west instead of east. And he sees it gradually go then down a little towards the track, towards the land. And he makes all of his measurements exactly what it did, and he describes that in his total frame of reference. Then we have another man who was standing on the track way to the westward as the train approached, and all he saw was this flame hesitate like this and go in towards the earth. It was just a straight line going like that towards the center of the earth. And he measured everything with his angle, azimuth, and his stopwatches. There's another man standing under it. As this happened, the train was going over a trestle, and there's another man standing below the trestle, looking upwardly and seeing this whole thing, and he makes his observation what he sees. You find out the total angles of observation, all the timing, everything came out. Each one was really very, very accurate and they all come out completely differently. And for this reason, Einstein then felt that all the circumstances must be reported, and not just what it is you happen to find on your scales there as you weighed the phenomenon, what went on within the test tube. This brought about Bridgman's feeling there should be a name for the inclusion of the unique circumstances which the observations are made. And he again gave the name operational, which he used to differentiate from a school of philosophy that was then been in operation coming from a man named Peirce at Harvard, called the school of pragmatism. In other words, it was pragmatic, but he wanted to use another word than pragmatic, so he was operational. Since that time, the word operation has come into very popular use in military ways and everything else coming from scientists, but that's where the word began. I am, in my geometry explorations, you see me getting into structures and so forth, discovering that the process of thinking produced a geometry. It was just the process of thinking about our experiences, and that our experiences were omnidirectional, so when you divide your experiences, all the ones outside, ones inside, it created a geometry. It just automatically produced a polyhedron or some kind of definition of what produced the insiderness and outsideness. So geometry has been developed by being very careful to remember at the outset, every way I can, what I personally was conscious of during when I participated in what we call thinking. And there are many other things I'm sure that went on that I am not conscious of, but the point was these are the things I was conscious of, and they led to a great many clues. So that's all operational procedure. So all of my geometrical exploration from there on is what I call really, it's all operational mathematics. I have absolutely no axioms. There's nothing that's said to be obvious, where our eyes are too superficial, because we now know how small the spectrum of the electromagnetic range of frequencies you and I can tune in. So we just cannot see adequately to say that's self-evident. Well, I find mathematics can play games assuming certain conditions to obtain, because I will not play. Now, I am an operational, and I often like to use the word experiential. I find that experiences can be inadvertent, they happen to us, and then there are the experiences deliberate. So I call one it is experiential when it's happening to us, and then I make it experimental when we manipulate the conditions arbitrarily. Now, in my carrying on with you, doing what I'm doing on this particular occasion, I'm almost 80, within a few months of 80 now, and I am operating completely extemporaneously. I do not have any notes, and I have made up my mind to, because we have tried it on several occasions before at various schools around the country, quite a number of years ago, where I was asked to exhaust my thinking, my spontaneous thinking, before a class of students, and where I would not repeat myself except to do important reviews to bring back in a strand of thought, which I'd introduce later, that you had to be conscious of tying it in. And I was asked to exhaust my thinking, all the thinking which both the class and myself agreed was not in the general way of thinking, where I had any sort of unique viewpoint as a consequence of my operational procedure in developing my thoughts and self-disciplines. In the previous experiments we've made, we had one that came to 52 hours, and because I am older, though I may be able to condense things a little more, we are all having such an acceleration of experiences as I opened with you last night, the input of information is so great that I probably will take a little longer now than I did before, so we made an allowance of about 60 hours. But I also have arranged out my affairs in such a way that I'll have the least possible intrusion into this pattern while I'm doing this, so that I will be able to really remember from day to day everything I've said over the total 60 hours. So I'm going to be really working on a mental tapestry, and I am introducing thoughts and so forth, and I'm bringing in threads, and you'll find me continually weaving, but working on the grand strategy I introduced you yesterday, working from the whole to the particular, the synergetic strategy, and requiring statements then of the whole, and then some of the known inputs, and finding out other things as we go. This is the grand strategy. So that's enough about the sort of operational statement about what you find me sitting up here doing. And because this is a very unprecedented affair, it's an unprecedented affair just to have this beautiful videotape. I don't know, you've been looking at the quality of the picture. It is really superb. And now videotape is able to do what you do with just a tape recording of voice. You can run it over again. We can come back later on where I've been talking about some object that we don't have models of, pictures handy. We can superimpose it back in the film at the right place. It is a very mutable and a lovely medium. And so we're getting a really very faithful recording of a completely live experience of you and I. And I had to have faces before me, human beings before me, so that I could really deal with their eyes, and I could not have people who came in and out. If somebody new appeared in the audience, I would then spontaneously, I want to bring him up to date with what the rest of us were thinking, so that we've had to have fairly clear-cut plans of how we would carry on here. I think all this is important to have in the picture. That's operational information. In other words, personally, I do not look upon undertaking such as somebody trying to create a beautiful moving picture, but they're just interested in the photogenics, whatever it may be, and certain dramatic moments, getting the audience to feel certain ways. Therefore, I do not go by protocol or any things that try to erase anything that seems to be any kind of a small marring item. I think all of those things are going to be very important operationally in whatever goes on here. Otherwise, we are all dealing in that extraordinary phenomenon called reality. Now, today I'm going to do some more reviewing of things in fairly large ways. There was something that is very much in evidence in the room here, and I have not talked about, and that it relates to our word structure of yesterday, and that is you see models around here with these compression members do not touch each other. If you triangle, you find these are flexible cables between them. They're not stiff little wires. They're not rods. They are literally completely flexible threads. And they are high tensile threads, Dacron, so they will not stretch. But we see then a complex of compression struts that do not touch each other. And the only thing that's continuous is the tension. Now, I became very fascinated as in my early days getting into structures and actually building things, and particularly dealing with boats and the very great strength of the rigging and strength of your ship compared to kind of strengths that are usually exhibited in houses. And the differentiating of the rigging of a ship into the compressional spars and the tensional cables and stays, halyards, all the things you operated the ship with. So I'd like to think a little about any structural system. We introduced those words yesterday, so now you know what I'm talking about there. We find that there is in the structural system, there was a complex of energy events which interacted with one another to produce a stable pattern. But some of them were trying to explode, some are trying to come to escape the system, and others are containing the system. And I find then there's this phenomenon of compression and tension that is always and only coexistent. I think lots of people say, I have just a compression member. Well, that compression member is at high tide of a compressional aspect, but does have radial tension in it. And we say, I have a pure tension member. It's not so. You find that tension is also coexistent with compression. To make that clear to you, I'm going to then point out to you, first I take a piece of rope, it's very flexible, and the only way that can give you any dimensional positioning stability would be when you have it tensed. So we take this piece of rope and our two hands and start tensing it. And the tighter I pull it, the more vigorously I pull it, the tauter the rope becomes. When we say taut, it means its girth begins to contract. That's so, as a consequence of my tensing it in this direction, pulling this way, it is contracting this way. That is, its girth is getting less. It's getting harder. You find it tighter and tighter. That is, the more I pull it, the more it goes into compression at 90, in a plane at 90 degrees by pulling. That sounds familiar to you from yesterday. That's precession. In fact, the pulling is, the result of this at 90 degrees. Now, I find that I'm going to take a number of rods, steel rods, and you find that they're very flexible. If I push it this way, they want to bend. I'm going to take a bundle of steel rods of eighth of an inch in diameter. They're 4 feet long, so that they're so long they're very slender and readily bend if I push on their ends towards each other. They're all the same diameter, and I'm going to bundle them together in parallel, one to the other, a whole lot of them. Find 2 of them will come into contact, I make cross section through them, they come into contact like that, and now they can't get any closer to one another, they're actually tangent. The third one will nest in top of the 2, makes it a triangle. I find that I can get 6 around one, making the hexagon form. We went into that pattern yesterday. I could get another row around and another row, and they get into this hexagonal pattern of closest packing. I take a very large number of these bundles, of these rods, and I've counted them out so they're going to come out in even hexagons, not just partial rings at the outer set. And taking them, bring them together, and finally, we keep doing this to them, they finally get in that closest packing, very much tighter than they were at first. Now I put a tensile strap around them to hold them in the closest packing. So wrap them all the way around the whole length of this. Get absolutely tightly bound together. Now, I made so many of them that we have a total bundle about 6 inches in diameter, and it's 4 feet long. So its length to diameter ratio is 12 to 1. We find there's something in columns, compression columns, we call slenderness ratio. The Greek stone column, they found they could go 18 diameters high before the column wanted to collapse one way or the other. That is the slenderness ratio of the diameter to length. And we have the steel columns could get up today, some of the very good steels can get up as much as 36 to 1. Before I would see what happens when you load a column in compression. It wants to banana like that. It tends to go to arc of decreasing radius. Now, 12 to 1. I made that bundle of 6 inches diameter and 4 feet long. So it's 8 to 1. It's a very short column, it be called. Has really no tendency to banana at all. It's pretty much like there's a stone section, one section in the Greek column. Now, I'm going to put this column under a hydraulic press. In the hydraulic press stream, top member coming down, fantastic power be exerted here. And as the pressure comes on each one of those each of the rods that's in there, you know they want to bend. But because they had closest packing, they can't bend towards each other. They can only bend away from one another. That's the only possible freedom. So that's exactly what they start to do. So they keep loading it, and they want to go out like a cigar quite evenly. We have something called the neutral axis of a compression member. If you can load it very closely on the neutral axis, then the load doesn't try to make it banana one way or the other. The slenderness could make it go almost any of the directions. A little tiny force goes that way. Now, we find that very evenly loaded at its center, and being a short column, it tends to just become like a cigar. All the rods on the outside can bend away from one another. That's the only direction they can yield. Therefore, as they do so, they were bound together, so it puts an enormous strain on the binding, because they work against that binding. So that while we are deliberately loading in compression this way, the resultant is it goes into tension in the plane at 90 degrees. It's exactly the opposite of what we did with the tension member going into compression. Here again, our friend precession. In engineering, that is called the Poisson effect. Now, often somebody's name being used really obscures a function, and it'd be better to say precession than Poisson effect. Then you really have the generalized principles covering all of these. Now, having recognized these proclivities of compression members, I saw then a tension member, when I do tense it, tends then to go to arc of greater radius. Here we have something really quite different from the compression member trying to go to arc of lesser radius. In fact, the tension member tries to straighten out and tries then also really to get all of its effectiveness within the neutral axis. It tries to get in its own neutral axis to be, in a sense, most effective. Tension members really tend to gain strength as first used, to build up quite a lot of strength. Now, I found that whereas there is a slenderness ratio in compression columns, there was no limit length to cross-section. There was no slenderness ratio in tension members. If you had a better alloy, they could be thinner and thinner. Yesterday I went into mass interattraction with you. This beautiful discovery of team play, really, of going from the Kepler and Galileo to Newton. And we have then, there is that mass interattraction. And when we get to alloys of metals today, we know that the atoms are literally not touching one another. They're just simply in closer proximity one to the other. I gave you the word synergy yesterday, and behavior of whole systems unpredicted by behavior of any of the parts considered separately. Chrome, nickel, steel is a very beautiful demonstration of synergy in physics and chemistry, alloy. We have a rule of thumb of a man of yesterday saying a chain is no stronger than its weakest link, and that seemed to be very obvious. By the same way, then, if I mix together a number of different chemical elements, our candy making would suggest that as when you could melt the sugar, then the whole thing comes apart, the nuts come apart. The nuts didn't fail, but the sugar comes apart. Whatever is the weakest element would be that, in the chain would be all you have to look at. The sugar in that peanut brittle, and so the sugar is the weak element. So, and peanut brittle will be no stronger than sugar. Now, when we come to the metallic alloys, things do not happen in that particular kind of way. I'm going to then take the chrome nickel steel And we take in the testing materials for their strength, the tensile strength per given cross-section area, some kind of cross-section area in America, square inch. The tensile strength of a square inch of material, so PSI, pounds per square inch. What is the cohesion of that material before it gets into two pieces? And that is the most prominent of all the strength testings that are carried on to learn about the structural strengths of materials. So I'm going to take when you're out testing, there is a point where the material will yield, and that's considerable time before it'll still carry quite a lot before it fails. So the engineering usually then deals in that. If you don't want to get to a yielding point, then things are going to be in trouble. So I'm going to take then the one is called ultimate and the other is yield. Stones, masonry for instance, have only about 50 pounds to the square inch tensile strength, the masonry itself. The stone is 50,000 pounds to the square inch compressional strength. So stone has had an enormous ability to carry loads, but no strength at all in cohering, comes apart. We have then metals taken out of the stone that have brought then tensile strength from the 50 pounds per square inch of masonry up to something like mild steel, primarily the iron, this is some carbon. This has a tensile strength in the commercially available materials, relative purity, that we get an ultimate in the mild steel of about 60,000 pounds to the square inch. As ultimate, yielding maybe around 50,000. We have the carbon, manganese, and so forth in there. In chrome, nickel, steel, the three prominent constituents are the iron and the chromium and the nickel. The chromium has a tensile strength of about 70,000 pounds to the square inch. The nickel about 80,000 pounds to the square inch. So the weakest is the iron of the 50 to 60,000. And you say then, well, put these things together, and the weakest adulterates the whole, like the sugar, and it can never have any more strength than the weakest component. That has been the everyday thinking. And for this reason, alloys have really surprised man tremendously, because society does not think synergetically. It assumes that all you have to know is about the parts, they add up. Now, chromium, nickel, steel, if I then get to I find that it does not come apart tensily in the tensile testing at the weakest, or where the iron yields. We find then that let's try the chromium side. Well, it doesn't come apart. Try the nickel, 80,000. We're going to say a chain is now as strong as the strongest link. And we find that 80,000 it doesn't yield at all. In fact, we don't get it to yield until we get to 350,000. Supposing I say, I want to try to understand this extraordinary phenomenon by saying, I'm going to say a chain is as strong as the addition of the strength of all of its links. Which everybody would say that's absurd. So I'm going to take 60,000 plus 70,000, that gives me 130,000, plus 80,000 gives me 210,000, but it doesn't yield till 350,000. Now, how does that happen? Well, this way it occurs. I want you to think then about geometries that I gave you yesterday of structural systems like the tetrahedron. I can take two tetrahedra of 4 stars each, and I can interrelate them symmetrically so that they're now 8 stars in critical proximity, and they take position at the 8 corners of the cube, with a cube having 2 tetrahedra in it, because each square face had 2 diagonals, and you could take the the cube and have the red set of diagonals. You'll find those are the 6 edges of the red tetrahedron. And have the other diagonal of each face, the blue set, that's the blue tetrahedron. You find the two come together with 8 points. Now, remember our mass attraction. These atoms are now in, there were only 4, and their distance apart was the edge of the tetrahedron, which is, on the cube is the diagonal of the face of the cube. Now, each of these 8 stars, the nearest one is the leg or the edge of the cube away, not the diagonal way. Therefore, the critical proximity has been very greatly increased. So each atom now has 3 other atoms in much closer to them than the original 3. So we have 4 cases of each having 3, and remember that the interaction increases the second power of the relative proximity. So the coherence has gone up enormously. Then we find that we have that cube now with the 8 corners. We find that there are 6 faces. So I can take an octahedron, which has 6 vertexes, and they'll exactly match the mid-faces of the cube. So each one of these elements coming in are just one of such beautiful symmetrical structural systems of atoms. So I then finally have all the interpositioning of them all within the same distance from the same common center. And we find the mass interattractiveness is just going up in this exponentially. That's how we got the 350. In other words, here we have an alloy is like the Milky Way. I take 2 stars in the Milky Way, and I'm going to have another star intrude halfway between the two, and the interaction is going to be 4-folded. But they don't touch each other. Now, I want you to then understand how that alloying is highly synergetic, and really appreciate that word. So I find then here's chrome nickel steel with its very high synergetic effectiveness of tensile strength. And these things really began to fascinate me very much. So I saw that tension members were not limited by cross-section in relation to length. If I could get a better material, I could make them longer and longer and thinner. That's exactly what went on in the history of suspension bridges. The first suspension bridges were actually made with great iron links, very great cross-section, very short span. We came to the Brooklyn Bridge, the first one where we're using cable, and used piano steel wire, which was one of those alloys. At a time when the mild steel was only about 50,000, and he got 70,000 with the piano wires. So we had relatively delicate cables carrying all that extraordinary traffic, this enormous span. Then when it came to George Washington Bridge, we've gotten very much finer because the alloys had so improved. And each one of these bridges are getting up Golden Gate and then finally Verrazano. We're down to very delicate cables. So you not only have greater loads and greater lengths, but actually less section of materials per given load. I saw that we're approaching, because there's no limit ratio of length to cross-section and tension, that we were approaching infinite length and no cross-section at all. And I said, is that talking nonsense? I said, well, because tension goes in, tends to curve arcs of very large radius, I better then think about some very big systems. So let's think celestial here. Let's think for instance, just the Earth and the Moon. And I see we can fly a little airplane right through the line between the center of gravity of the Moon and the center of gravity of the Earth, and nothing happens. You don't sever anything. In fact, this turned out then to be the scheme of the universe, where nature was using discontinuous compression and only continuous tension, which was invisible to you and I, because this extraordinary mass interaction, which is invisible, which made it so perplexing what those planets were doing to the early observers. Now, may I have some water? Will you bring me a piece of paper? You're going to have a little blemish here. So, there's a piece of paper. I'm Sorry, you better make a cut. Thank you. Right, sir. That's all, sir. All right. Apparently, then, the great structural scheme of the universe, I found these enormous masses interacting one another, the Earth and the Moon, with enormous distances between them. Then thinking a little more about what you and I have just reviewed about compression and tension, I would notice then that when I load a column, I must try to stay on neutral axis, so it will not tend to bend one way or the other. Then I see that loading that compression column, it tends to be more and more of a cigar, and find if I keep loading it under the press, it's finally going to get to be a sphere. And the spherical moment, something extraordinary happens because any axis is a neutral axis. Up to this time there have been only one neutral axis, but suddenly any axis is a neutral axis. So that we found that ball bearings, spherical sealed balls, became the best compression members man had ever invented. So they carry these enormous loads and continually distribute their loads, so any aspect is neutral axis, so any aspect will do. And they're continually serving as you roll them around. So I found that nature was compressionally optimal and the spherical. So then I said, here's a scheme, here's that Earth is a sphere, and the Moon is a sphere, and the Sun is a sphere, and you get the atoms, all of the what nature has is islands of spherical compression in a sea of comprehensive tension. So we have then what we call discontinuous compression and continuous tension. There's a scheme of nature. And man was not building his building that way. Man was building entirely compression on compression, brick on brick. Didn't see anything of any other kind of logic. This made me wonder whether it would be possible to make discontinuous compression, continuous tension structures. That's really what opened up this whole field. There are very many people now dealing in these structures, but I call them tensional integrities. The integrity is in the tension because it is continuous, comes back to itself. It's always closed system. When it's open, then it'll make trouble. There must be closed systems. And then I shortened the words tensional integrity down to tensegrity. So we call these tensegrity structures. Absolutely even distribution, so they sound same sound when you're trying. If you tighten one of them, they'll all tighten absolutely evenly. And that's like any pneumatic ball. when you fill the whole ball, all the loads distribute absolutely evenly. So all the pencil enclosure. Now these are odd balls, but you can see the holes in them. All balls do have holes, and they're too small for the gases molecules to get out, but they're full of holes. So this is simply really a pneumatic structure. We'll go into that just a little bit more. But mainly I want to get to nature's scheme of discontinuous compression, continuous tension. Nature uses tensegrity. And I find then nothing could really make clear to me the degree of inefficiency that is imposed by man's non-synergetic thinking and his feelings you have to have brick on brick, the stone on stone on stone. This taught me that I could possibly do much more in closing and be much more effective structurally, employing the omnitriangulation, paying attention to all the things I've gone into with you about quantums of energy in the structures, the 6 vectors doing that, which of each one being push and pull, the 12 are always there. Because they're both positive and negative, each one of those 6. So there's a fundamental 12ness there. Now, I'm going to go into another mental exercise with you regarding schemes of structuring of universe, and I began to think then about, for instance, just I always find social insights that seem to accrue to terminal information such as I'm giving you. We do find out what is the optimum, that the sphere gets then to be the optimum for compression. And the tension going unlimited to no cross-section at all. And this is really the whole scheme of our universe. That is our gravitational interaction. I find then, for instance, it is very interesting that in the regeneration of human life, the general design of the human beings, of the female and the male. I find the female having then the eggs within her, and the eggs are fertilized within her, that the new life of the female continually comes out of the female. She opens up, and a new life comes out of that life, and a new life comes out of that life. This is not dissimilar. In fact, it is the same principle that was discovered by Goethe, the German poet, scientist, very much of an expert in a number of scientific subjects. But he was the first to point out that vegetation, that the tree is a wave phenomena. I'm going to bring together several things now that Goethe did not, but you and I can put together from the experiences we've already had in this room, where we came to the discovery of a tetrahedron being the simplest structural system in the universe. And I want you to think now about, for instance, a Greek column, and think about putting this piece of stone on a lathe and revolving it in order to get it round. They had different tricks of making them round. So the top of the column is the same diameter disc as the bottom of the column. I'm talking about only one piece of that stone. Now the fact is, that stone has very high compressive capability. We found that it had 50,000 pounds to the square inch. Supposing now 50,000 pounds, that is 25 tons. I would like to carry a 25-ton load, and I have a Greek section of a column, one piece of stone has been made it's a cylinder of stone. And I find that what I can do is to have a load of 25 tons. So if I just mark off in the center of the top of the cylinder a 1-inch diameter of an area that has 1 square inch. Then I'm going to take that stone from that top and then going down to its base, I can keep shearing off till I get a cone of stone. And there's at the top there enough cross-section to take care of the 25 tons. All the rest of it gets stronger and stronger. But because it has keep the base, it is stable, as the tetrahedron is, the three-point landing. This is very important. We've got to think about that now. If I have this standing by itself, it tips over like that. If I have two of them standing, they can tip over towards each other. They might tip anyway, but I can let them tip towards each other. And if I do that, I wish I had another stick. I'm going to just do it with my arms. Here's a column and another column on my knees, and they fall towards each other. Now they have 2 points on the ground. They act like a hinge. They can fall this way, that way, but only in a plane. Before, they could fall any direction. Now they can only fall, articulate in a plane. Now I'm going to have a third column. 3 of them are loose like that. 2 of them fell together, and the third one fell towards them, and suddenly they come together and get our tripod. And for the first time, we have stable. We cannot have the stability until there are the 3 of them. Those are then the 3 legs of our tetrahedron, but as you load them, they want the thrust to come apart. So we find we have a tension three tension members are a finite or closure. You must actually be close the ring at the bottom, and they can't come apart anymore. So we have the three compression thrusts and the three tensions keeping them thrusting. So we have in that stone cone now, I have enough compressive strength for the 25 tons, which is a whole lot. That's a big 25-ton truck, a very big truck. And we can carry it, and that's simply chisel well over us. That stone is unnecessary. The base is wide enough then to give me that 3-point stability. So it's a cone, and I find I go even further. I pick 3 points on the base, 120 degrees apart, and I can then massage away, cut away the cone to less than a tetrahedron. And I have all the stability and all the compressive strength. It finally gets down to a tetrahedron. Now, the Greek column, they will out, in a sense, empirically, that's deep in with you. And human beings are just fooling around with sticks and coming to tripods and so forth, they did long ago, and campfires and so forth, what they can do with pieces of wood, handies, twigs. Then there's necessity from time to time for the load that you're going to carry is more than just that 25 tons, so you want a wider section. So we really can get that with an octahedron. Remember, the tetrahedron then had the beautiful wide base for its stability this way, but the octahedron has an equal triangle at the top. So if we had a full load which we want to use this much as our cross section, we could use the octahedron and it would take care of both, because then we find the octahedron is a very interesting set of conditions. Here's a load. These two are falling towards each other. You have all those set of hinges in there. And everything is in optimum position of comfort about the thrust. So that we really have two cones or two tetra point to point producing this kind of instability. Now, I wanted to introduce then this stabilization of columns and the tetrahedron and give you a little feeling about, I said, the poet Goethe introducing wave phenomena into concept in a tree, and the Goethe didn't talk about the tetrahedron, but I point out to you that if all trees grow, there is actually then the top of the tree of this year, and we have the cambium lower. So each one is a cone around. So the next year is a cone on the outside of that cone, series of cones. And in fact, we find that if you still to the pair away, and the tree does, many of the trees you'll find is literally the tetrahedron there. There are three main roots going out like that. And there's three facets here coming really to a cone. So the next year is a little larger tetrahedron on top of it, and another tetrahedron on top of it. We then get to where the branches are also tetrahedron, have something called the wing root. And the bottom of the wing, you have the 2 points at the top of the hinge part, and then the member coming down near the bottom, and the wing root. This is just a tetrahedron, 1 point down and 2 on the top for the hinge. That is wing root of all great branches of trees. So we have a cone coming out from a cone. So we have coming out of this total surface here, the cambium layer suddenly breaks open into a new tetrahedron going out of this branch. And on that branch breaks open a new tetrahedron again, keeps opening up. The inside is coming out, and it gets to be a twig. And then on the end of that twig you see the bud, and the bud keeps opening up, and the leaves coming out, and out of it comes then the blossom. And then center of the blossom gets fertilized, there's a fruit. Finally, out of the fruit comes a seed, and finally it goes off. But Goethe pointed out this whole thing is a wave thing, opening from inside out. I want to bring back then, I spoke about the female, and the new life is on the inside, continually coming out, and the new life comes out of the next female. It's a continual opening up wave. I also then point out to you the difference between the male and the female. Because the male then becomes discontinuous. He comes islanded. He's a hunter. The female and her young so forth are in great continuity, that family. but the male goes off to be the hunter, the fighter. He's islanded. She is central. It's really very fundamental in social behavior. Now, I just personally find that the woman is tensive, just fundamentally, just the act, the sex act. She pulls in, and the man is compressive. He thrusts, she pulls. And it's just very fundamental to what we call being female is to pull, to walk away, to attract. Find the male tending to do this, to punch. She does the other way. I can't help but find it very important to notice these things this way. I don't see any pure males or pure females in human beings, so there are all kinds of often males can get to be quite attractive as well. They do have the attraction, but the point is that there seems to be a predominance of this time, and has something to do with the great integrities of the fundamental complementarity I gave you yesterday, where we only just learned in our last lesson, less than 20 years, less than a score of years, that the complementarity is dissimilar. It is not mirror image. So the unity is plural, and at minimum two I began to find to be a very fundamental way of thinking, and that was a phrase I began to adopt long ago. And I was told at the time of World War II, when the Manhattan Project came along and physics was trying to understand a great deal, that my use of the words, this phrase, that your unity is plural and minimum two, was then ventured into by the quantum physicists, and they found it suddenly opening up all the doors. They had to get in that fundamental two-ness. Now, you are experiencing with me a sense of the incredible interrelatedness of our total experience. And yet the apprehending, comprehending, incisive comprehending of the differential, of the intercomplementations. I'm going to go a little more into that tensegrity and think about it. I find it's been extremely interesting to me in my experience with the structures and humanity and their building, that the only reason that geodesic domes do what they do, as they get enormous spans that we've not been able to get into before, the lattice clear spans of man have been way transcended by the geodesics. And they apparently can go on to any size because they are tensionally coherent. And compression is discontinuous in the fundamental principle of the structuring itself. So that tension has no limit to size, just as you can have the interrelationship of the galaxies at those millions, billions of light years even apart, and still have the intentional integrity. So there's no limit to the size of tensegrity structures. All the engineering of society built then on brick is entirely a compressional strategy. Engineering has taught, structural engineering has taught, is a compressional strategy. And it is thought in the terms of the Earth being a compressional unit. You dig a hole in the earth and you take a solid compression column and you put it down the hole and you fill your earth in again. Now you simply have sort of formalized compressional extension. You find that mass that is standing there can also, that if you can hold the ends of it, as the wind will, acts like a lever and can pry it loose. So what man then did, having developed a compressional continuity of the earth and a compressional column, he then took tension stays, a minimum of 3, and suddenly found they could offset the wind with that tensional member making our friend the tripod, but in tension. And find then men building boats. So they had a solid, they thought of the boat as a solid compression continuity. They stepped the mast and they then put tension stays. Compression is primary and tension is secondary, a helper. The mast will stand up all right by itself, but if you can really put real loads, take great wind loads in your sail, then you have to have the tension stays to give it greater advantage. So there are enormous numbers of those stays at every level in the great square riggers. You see set of stays making short mast sections, because between the sets of stays is a full column length. Now, as you look at square riggers, then you begin to feel the tension and compression logic that I've been giving to you. Now, in thinking about then the engineering that I have experienced, where there have been a number of large buildings to be built with geodesics, and all of them have to, if they're big buildings, all have to be processed by engineers. I have to bring in consulting engineers who are certified for that particular purpose, and I've been able to get some extremely good ones in Boston, Cambridge, and they've gone through a great many buildings with me, and we have to then go through building departments and meeting with the engineers who check the work that's going to be installed. But the engineering logic then requires a complete, paying no attention to anything but a compressional continuity. As I said, tension can be a helper, but it's a compressional logic. It is not a tensional logic with compression as local helper, which is the way the universe is put together, both microcosmically, macrocosmically. The engineers who work with me now really finally come to realize that the tense-segment structure is the explanation of the geodesics, but it's not in the engineering teaching as yet. It's not in any of the codes, and therefore it cannot be participated in. This made me realize I could get into very much lighter buildings. But I wanted to get the engineers into a strategic position to be able to take advantage of the tensegrity. And I have recently written a paper, and here's the paper, and I think it will greatly help, because we can go over to another form of engineering, which is called pneumatic engineering, hydraulic engineering. Some fundamental qualities now that we're going to find again regarding structures and our minimum or basic structural systems of universe of yesterday. I want you to think now of tetrahedron again. I've read tetrahedron. I'm going to take two tetrahedra. There could be an octahedron and a tetrahedron. They could maybe join something like that. I could have then two of them. This is the hinge. This would be a universal joint. As long as there's some kind of pull between them, there's a mass attraction, so they can't come apart, so it acts very universally. Now I have a hinge that could only do this. Three of them touching each other now becomes rigid for the first time. Linus Pauling, great chemist, received the Nobel Prize twice, once a Peace Prize, but the first time was as a chemist. And Linus Pauling's Nobel laureate paper reviews the history of chemical structures, with chemical structures. And he goes back to the first one of the chemists who had noted certain, just like the early human beings noting that 5 lights in the sky behave a little differently from the others. We have chemists then noticing in organic chemistry certain things going on where there seem to be an abundance of numbers 1, 2, 3, and 4 in relative proportions to the way things are disassociating. A man, Frankland, and he is a relatively short time ago, just at the end of the 18th century. And early in the 19th century we then have Kepler and Cooper, and they make a little more of a discovery of the relation to that oneness, two-ness, three-ness, and four-ness. Then there comes a Russian scientist operating in France named Butlerev. Butlerev was the first to ever use the words chemical structure, and he related then to the oneness, two-ness, three-ness, and four-ness, And he spoke about these as bonds, and being in France, the bonds, it was the word valence. And there was single valence, univalent, and bivalent, and trivalent, and quadrivalent. Now this valency, then incidentally, there was a 35-year hiatus, no more progress in chemical structures after butyrophin. Suddenly a man named Van Hoff, a Dutchman, came along, and he said he thought that the oneness, two-ness, three-ness, and four-ness had to do with the tetrahedrons, four points and four faces. He was called by all the chemists and other scientists charlatan, a rogue. He was called every horrid name you could call a human being. And he was not daunted. He went on. He was able to give optical proof of the tetrahedral configuration of carbon, as the first chemist in history to receive the Nobel Prize. Now, we have then the tetrahedron suddenly entering into our chemistry here, and our phenomenon of bonds and valences. So I'll simply give you then, this would be univalent, this is bivalent, trivalent, of all four of them together, the two tetrahedrons nesting in one another, congruent with one another, and that's quadrivalent. And really the difference between a carbon, I gave you yesterday, I took the vector equilibrium, turned it into four tetrahedra, congruent with one another, do you remember? It was quadrivalent, and this was like the difference between carbon, soft carbon, and carbonous diamond, when it gets to be quadrivalent. We have then, I mentioned yesterday, in the grand synergetic strategies of the known behavior of the whole, the known behavior of some of the parts, finding about others, and going through the Greek triangle, and then Euler's beautiful topology. Then I said Willard Gibbs introducing in chemistry the phase rule, where he has a relationship between chemistry and its liquid, its crystalline, and its gaseous state. And we found that Willard Gibbs' phase rule had to do some way, and looked like the same kind of a formula as Euler's. This plus this equals this plus 2. And I'll then give you that the liquids, I want to go in the gases. I'm going to take a number of tetrahedra, the same size like this, and I'm going to fasten the tetrahedra together corner to corner. So this tetrahedron touches one another. And then the next corner here goes another tetrahedron. They're continually interlinked as each tetrahedron touches one another, each corner touches just one other corner. If you do that and make a model, you find there's a whole lot of space in between them. And they will flop around as a total aggregate, and they will fold into one another. They act very much the way, these are the way gases are highly compressible. There's an interlinkage, there is a viscosity, there's an integrity, but they're highly compressible. But the gases distribute their loads due to the flexibility. All loads are immediately distributed. So they have air in a tire, or air in a balloon, or air in a football, and just punch it in one place, and that air immediately distributes the load to all of the tensile enclosure, absolutely evenly. So a great truck can have only very few pounds of pressure in the air inside, because it distributes it so perfectly to the whole load. And the bigger the casing, then the more tensile surface it distributes to. So we find then pneumatics consist of these univalences. I'm going to say take the tetrahedron and fasten each one to another tetrahedron, but two of them touching, the hinge between them. When I do that, I'm going to go and get this tetrahedron in the corner. Well, I can reach there. We find each one of these tetrahedron in here, the tetrahedron here, are touching another tetrahedron at 2 points. They are edge to edge to one another. Here's a tetrahedron in here, and it's edge to edge with this tetrahedron here. When you do then, when the edge to edge, then it fills all space this way and seems to be very stable. This is exactly like the liquids. the liquids are non-compressible. They're already in the form of the closest packing, so it can't be compressed any further. But because they are hinged together, the hinges transmit loads. So liquids transmit any load at any one point is, as with the pneumatics, distributed to all of the tensile system. They enclose the liquid. Then when we get to trivalent, then for the first time, there's no hinging, no universal joint. They're absolutely rigid. They no longer distribute loads. Now, these are the fundamental qualities. The crystalline, just absolutely rigid, does not distribute loads. The liquids distribute the loads, and the gases distribute loads. But the gases are compressible, and the liquids are not. This brings about a very important way to think. But I've got you now thinking about a tree as a set of tetrahedra coming out of tetrahedra as basic structures. But also then we find what makes a tree able to do what trees can do. If you ever try to pick up any great weight, let's take a 30 or 40 pound suitcase, and you try to hold it out horizontally, and you just find you can't do it. And yet you'll find a tree holding out a branch, and some of these branches, if you weigh them, get up to as much as 5 tons. 5 tons horizontally in a great wind, and yield to the wind and not break off. It's fantastic structural capability. Man has never done anything like it before. Well, it's done by a very simple way, because nature then has, in the crystalline, you have triple bond, therefore you have the greatest tension. The liquids have 2 bonds, they're a little more viscous, more tensile strength than the gases, only 1 bond that comes back. So that the greatest tensile strength is accomplished by the crystalline. Therefore nature ships in a seed the instructions for further crystal production. And you produce the local crystals with the local waters and atmospheres and the local chemistries. So these crystals grow, and the crystals act as then sacs for liquid. And so the tree is just filled with the liquid. I gave you yesterday the tree also having to have roots so that it could not blow away when exposing all that leafage to take on the sun energy impoundment through photosynthesis, so that we had osmosis, and the water goes only one way, valving both of the roots into the tree to fill all these sacs. So the tree is using the crystalline entirely in tension to enclose the liquids. And the liquids then completely distribute the loads throughout the tree. They valve it out in the sky just bit by bit to turn it into more rain to come back in more trees, so more of this process can go on elsewhere. But the water is entrapped in there, therefore it distributes its loads locally. So there's then this absolute non-compressibility of the liquid, and distributing loads make that tree able to do this extraordinary task. If we get an ice storm, off comes the branch. Can no longer goes crystalline, cannot distribute itself. Men have not built any buildings in that way. They've used entirely as a crystalline continuity concept of compression on compression. So as yet our building is incredibly inefficient. And so I'm now trying to understand a little about what goes on in tensegrity structures, and I will come then to the analogy with hydraulics and pneumatics of load distributing, because we do have continuous tension and discontinuous compression. I want you to think about what goes on inside a sphere when you blow it up. Let's say it's a basketball, be a balloon. You keep introducing more air. There are then molecules of the gases, and you're getting them crowded in there. Now, all these gases are full of fundamental kinetics, and they're continually going like this. Remember, every action having its reaction and resultant. So every little molecule of gas that is going somewhere in there does it by shoving off from another molecule going the other way. Think about 2 swimmers. You probably have done swimming in a tank, all right, and you dive and you get the other end and you double up your knees and shove off from there for the wall, go out again. But two swimmers can meet in the middle of the tank and shove off from each other's feet, like that, double up, and then off they go, using the other one's initiative. This would be typical with the way molecules are behaving in pneumatic structures. Now, we find that the molecules then are not simply going, they don't go to the center of the sphere and then explode outwardly. This would be a pulsative affair, take time to get it, and the thing would be vibrating like that. They're not doing that. They are ricocheting around inside. So if each one is starting to go this way, another one goes that way, and the two hit the wall. And they can't go no further. They push the wall outwardly, and then they bounce, ricochet off, and hit the wall again. So it came acting like little cords inside of the sphere. Now, also then introduce another principle, which is dealing in great circles and spheres. And the word geodesic. Geodesic means the most economical relationship between events, between any two events. The great circles on spheres are geodesics. That is a shorter distance between any 2 points in the sphere on the great circle than it is on any of the lesser circles. A great circle is defined as a line formed in the sphere by a plane going through, cutting through the center of the sphere. The equator is just such. Each of the planes of longitude go through the center of the sphere. So those are great circles. I want you to, we have then on here also lesser circles. We have the latitudes. They're not great circles. We come up here to 80 degrees north latitude. I'm going to take my dividers and open from the pole to the 80 latitude. And I find that I strike this little circle. I got my dividers fixed at that opening, and I go down to the equator and put it on here and strike the same circle. So we have then the equator running like this and the circle superimposed on it. Where the little circle, lesser circle crosses the big circle at A and B. And you find it's much shorter distance between A and B on the equator than it is going off the detour of 90 degrees and then coming back this way. I just want you to visualize quickly how great circles are most economical between points on spheres, and the chords of great circles are even more economical. And nature always does the most economical. So we find that the molecules bouncing around inside the sphere will not go around in latitudes or lesser circles. They just automatically have to get into bouncing into great circles. That becomes very exciting to discover. So they're not just going around in layers. If they're going around in layers like this whole thing is flattened down very easily that way. And it has always omnidirectional stability due to the fact it is using great circles. Now I get one great circle around here. And we find that every great circle crosses every other great circle at 2 points. So that this great circle longitude crosses then the other longitudes at the North and South Pole, always 180 degrees apart. I got a great circle here and another great circle there. Then I got suddenly a third great circle, the equator, and that makes a triangle. North Pole, equator, equator. Now we found 2 is unstable. And something I didn't say to you yesterday about the necklace and the triangle that I'd like to introduce right now because it's very, very relevant to the understanding about that triangle. I said, why and how did that necklace consisting of 3 compression members, rigid, and 3 flexible tension corners, how and why did it stabilize this pattern? I find that any 2 of them coming together are fastened one to the other. They're like a pair of 2 knives of a pair of scissors with a common fulcrum, a lever. And the further you go out on the lever arm, the more effective those shears are. Therefore, if you want to have bolt cutter, you can go way out very long arms of good strong steel. So we find that each side of a triangle compression member is taking hold of the ends of the 2 levers and with minimum effort, because it's on the end of the lever, stabilizing the opposite angle. It's very, very exciting to see how beautiful, again, this least effort that is being demonstrated by that necklace triangle. Coming back then to triangles and understanding it, is the third side that stabilizes the opposite angle. So I had two great circles crossing each other at an unstable angle at the pole here. But the minute the equator crosses it, triangulates it and immediately stabilizes it, because we have these interference patterns going on here, and this sets up a triangle. Then the fact that there's one triangle, then you find that automatically then makes, I said I had the equator and I had these two here, and then suddenly you get the octahedron shows up. It automatically makes the octahedron. So I get four triangles, eight triangles here. And these triangles, even though the first two may have been some odd angle like that, not full 90 degrees, and the second where the equator cross maybe not, but because there's a very high frequency interference here, they keep trying to average. They whip back towards the octahedron. We find then this same thing happens with the icosahedron, where we have 6 great circles instead of the 3 of the octahedron. And these 6 great circles, here they are. And here are the triangles, where you can see them getting to the point they can't get any closer to the triangle, can't go that way any further, and it can't go the other way, because here is a triangle up here. See this triangle? And this triangle down here. And these are gone spreading to the center of the center of gravity, each of those triangles. All the variables are in there. These would then represent the ways in which, I said, the icosa gave you the most volume with the least energy investment. So again, this least effort. We find then fundamentally the molecules of gas inside of a pneumatic structure get to doing exactly the pattern you're looking at here. This thing you're looking at, incidentally, is called, in the British Museum, the oldest toy known to man. This particular one came from Rangoon, and through the Thailand and Rangoon, these are used instead of pneumatic balls, and they play and they hit the balls, and this bounce beautifully. It distributes those incredibly beautifully. So now I have here a very fascinating matter, because I found that the pneumatic structures are producing icosahedronal great circle interaction patterns. This hit me very hard, and because it was a pure geodesic structure, and I received a letter and some photographs from 2 scientists of General Dynamics quite a few years ago, and they were 2 scientists who were working on re-entry cone problems for the rocketry and space vehicles. And you get in this enormous heats of re-entry, the frictions and so forth. They were trying to get they were making experiments with titanium, which is where we get the greatest lightness and very, very high strength. And they made 2 hemispheres of sheet titanium. One about a half inch less in radius than the other, or the other was an inch less in diameter, and they had one concentric with the other, and they sealed up the base between the two, so there was a half-inch space between these 2 hemispheres. Then with a pneumatic pump, the vacuum pump, they pulled out the air existing between the 2 thin shells. This meant that the bottom, the inside, the smaller shell, the atmosphere was able to get inside of it. And coming inside of it, it then pushed the inner sphere outwardly, because the atmosphere came inside the sphere and pushed it out. But they exhausted the air between the 2, therefore the same atmosphere on the outside of the outer sphere pushed it in. And it dimpled in onto absolute just this pattern, the pure icosahedron. And they found that what we call the frequency of the modular subdivision depended on the relative thickness of the metal. If we made the metal thinner, we got higher and higher frequency, tensegrity, icosahedral geodesics. They thought I'd be pretty pleased, and of course it was. Now, what I'm coming to then, the way we really explain geodesic structures must be hydraulically rather than as crystalline, because the crystalline structures do not distribute their loads, and these do. the very beauty of it being the fact that, as I say, if you tense any one of them, they'll come out the same tuning all over. Next. We've got quite a lot of interconnection here today. Begin then to think of a universe in which there are great potentials to humanity, and we immediately have great insights that man is then accomplishing tasks he needs to do, building such as we're in here today, looking at great cities, where I now know that, actually experimentally, that I can give you 300 buildings for one for the tasks they have to do against the best known alternate engineering strategy than just the one thing, tensegrity spherical structures, where spheres in their own right enclose the most volume with the least surface. You have to pay attention. Now, I hope, and I'm saying this right now in our meeting, because I want you to begin to feel with me as we explore more and more. You find openings all around with problems that have been, you know, that are facing humanity. We begin to see there are options and outs that he's not employing. As you begin to add up those options and outs that he's not employing, you suddenly discover it's highly feasible to take care of all humanity at the highest standard living anybody's ever known. And I know, and this is when I'm talking about big patterns, little man on our planet, not working on cosmic accounting, but having started naked, helpless, ignorant, finding his way by trial and error, is still at a level, sort of average error of viewpoint, which is perfectly logical. There's no bad or good man in here. You can't get anywhere in your thinking if you impute malevolence to individuals and so forth. I find then that it is then still assumed by humanity as self-evident that there's nowhere nearly enough life support to go around. So people are always worrying about that population of people are ends, worrying about all these other people coming around to jeopardize their peaceful stability or enjoyment of their advantage. We have then, because it's a working assumption there's nowhere nearly enough to go around, this is why we have politics. Each political and politics are inherently biased. They simply say there's nowhere nearly enough ground, but I have the most logical and fairest way of coping with fundamental inadequacy. It's a horrible matter. But if you come along with me, you're going to get a better chance of carrying on, and your family have a better chance of surviving. That's the only reason we have politics. And you're automatically taking an absolute lethal bias is going to be your side or the other side. Gradually find man can do a little more, so he said, well, you and I get together. Apparently both of us can get on all right, so we get a little larger groupings. And all of humanity finally enormous blocks of now possibly 3 or 4 major groups saying it has to be you and me. But beginning out even 2 great big ones, you and me. And for this reason we do have then the great nations of the earth annually. For the last 2 decades, the United States, China, Russia, NATO alone, their appropriations annually, sum total more than $200 billion a year, getting ready to kill. All the highest capabilities of man being focused on how do you kill. On the working assumption, there's never enough to go around for everybody. That's why there's no use in having social legislation. If there's no expenditure you can make, you're going to take care of everybody. So you don't try to spend it that way. Wonder why politics can sometimes seem to be so cruel in not taking care of the poverty. They say there's just not enough. Well, I now know, I really know very well, and I'm sure when you finish with me, you will go out and do a lot of checking, but you will have gotten many insights in the direction where you could see what I'm saying could be true. I'll just give you something very simple in the relation then to that structure and environment controlling, man developing environment controls for humanity, where you don't want to have something as an insulator. You want to have a prison. You don't want to have that Greek sphere and there's no traffic between the two. You want to have some kind of environment control so where what you need can come through when you want it. It's a sieve. Must be a valve to then not try to insulate you. You need water to drink, but you can't drink it all when it rains. So you want to have a holding pattern where you then interrupt, shunt, and hold and valve into your presence in the magnitudes and frequencies that correspond with our needs, while also being utterly thoughtful of the rest of the ecological balance of all the other things that have to go on if human beings are going to go on. So that water can be very, very well handled, and just a holding pattern, because gravity is pulling it in, so you just don't let it move that fast. You run it through all the useful channels necessary. So I see then environment controlling is a valving phenomenon in which we have things coming at us in all directions, like to have an omnidirectional environment valve that can cope with the various frequencies and magnitudes of all the things we want to intercept and turn to advantage. It's a very different way of talking from the whole architecture or something that's going to give you distinction out on Main Street, whatever it may be. Or something you're going to make money out of. We're talking about how do you make life work and trying to find out why humans are here and what we ought to be doing to abet why we're here, and how we employ the principles we're discovering in the most effective manner. I think it's a good time for a break. If you don't mind, another just 10-minute phenomena. We'll start again at 2 minutes after 8. So I talked about the grand strategies of all political systems, assuming it has to be you or me, and the enormous commitment towards the negative of the killing. And this really is opposite of synergetic. It is really me or you, rather than realizing there could be something when you and I get together. Doesn't make any such allowance. And I'm also gradually exposing to you grand strategies of nature's way of solving problems, showing that she has principles that are operating in the universe, that she always does things the most economical. She uses the most efficient. And you and I, having been born naked and helpless and finding our way, doing many inefficient things as we go, simply because we do have a prime built-in drive of hunger, procreative urge, thirst, curiosity, all these built in. We're giving this programmed so that we'll do it. And so we were, I say, quite clearly designed to make those mistakes, but also then designed to be able to discover principles and to discover that you can be more efficient and nature is using the most economical. So that as we begin to get a little closer to nature, which unquestionably means getting considerably happier, that we're going to find ourselves getting considerably more efficient. And I just want to be aware of that as I talk. When I talk about the biggest kind of patterns, I introduced to you yesterday the idea that nature is doing some very big things, even that society didn't know were going to happen. I've introduced you to society having a vanity, and once it happened, not really having the beautiful lesson it really could learn if it realized how completely it did not anticipate that. Therefore, society would not be assuming it was having to find all the answers right away, that to realize the universe is getting along pretty well, and we may be able to check in. We may become members of an operating system that where we begin to really consciously participate, employing our higher faculties, really get on with the universe. We may have such a function ahead, but we have not qualified yet. We're embryo, and I'd like you to keep feeling that as we go along.